Swayam Prabha. Digital India. Educated India.
Hello and welcome to Introduction to Machine Learning. In this module, we will look at advanced neural network concepts. So some of these will be going into the realm of deep learning, which is an advanced course, advanced subtopic within machine learning. So we will not cover a lot of these in depth, but it is good to get an introduction to these concepts when you are studying neural networks, because a lot of recent advances and research is focused on advanced. So the learning objectives of this module are that you should be able to write neural network loss functions that are for slightly more advanced ML problems, machine learning problems, than what you have been used to till now. You should be able to write some properties of natural signals for which special layer architectures of neural networks are useful, for example convolution and pooling. And you should be able to explain the reason for exploding and vanishing gradients in neural networks that propagate gradients to through many layers, and then see how long short-term memories can actually resolve some of those issues for recurrent neural networks, whereas certain other architectures such as residual networks can do that for convolutional neural networks. So let's start with slightly more complex problem than what you have been used to. Let's start with a multi-output regression problem. So here the setting is such that you have a target Ti, which is a continuous value, but it is not a scalar, it is a vector now. So for example, let's say you have T, I will try to draw it bold. So this is bold Ti, right? And basically this is a vector of several Ti1, Ti2, etc. So it has Ti1, Ti2, these are the scalars, and all the way up to Ti, let's say D, right, capital D. So this is the dimension of your target output. So what this an example of this could be that, let's say we are trying to predict the height and breadth of a particular object in an image. So image is the input, but height and breadth, both of these, or height and width, these are both continuous values. So one will form Ti1, the other will form Ti2 for the ith object or the ith image, right? And the neural network predicts y, and this y is also a vector, it's no longer a scalar. So this is also bold, and we have yi. Okay, so between yi and ti, what we want to do is we want to reduce the difference between yi and ti, and now it is not going to be a scalar difference alone. So we have yi also as a vector, which is yi1 all the way up to yid. Okay, so now the loss that we will use for this neural network, let's look at that, but first let's look at what the architecture will look like. So let's say we have inputs. So these are your input neurons. So this is xi1 all the way up to xi, I will use small d, all right, and then you have some hidden layers. Okay, so this is fully connected, all inputs give feed into the next layer. Okay, and then we have yi. Okay, so yi1 and yi2. Okay, so this is yi1 and yi2. There are two outputs now, and each of these neurons in the hidden layer and the output layer have one bias each. So this is your yi1 and this is yi2 for the ith input. Okay. So now the loss function that we can use for this is based on L2 norm of the difference between Ti and Yi. So we will take Ti minus Yi, right, and we will take its L2 norm, okay, and we can square it, alright, and then we can take half of that, okay, and we can sum it over all I, and then we can divide it by n, which is the sum of which is the number of training points. I ranges from 1 to n. So this is going to be the equivalent of mean square error, but for vector output. All right. So if whenever we have multiple outputs to be predicted, then we can use a loss like this, which is a generalization. Now here we don't have a simple difference, we have a vector difference, and then we will take its L2 norm and then we can square that. So basically it is going to be, in some sense you can think of it as sum over I, sum over j, right, and then we have Tij minus Yij squared, okay, and this we will have a half here, and we will divide this by both n and d. Okay, so that is going to be the equivalent of mean square error in multidimensional regression output. So now let's take this idea of regression losses a little bit further. So if you remember the L2 losses or this mean square error, so this mean square error, if this is your error and this is your loss, the profile looks something like a parabola. Okay, that's your L2 loss. And the problem with this, or first the advantage of this is that whenever the error is small, the gradient is going to be small. The near the origin, the gradient of the loss is nearly zero from both the positive and the negative side. So for small errors, it's not going to make adjustments to the neural network. They are not going to contribute to the weight adjustments. But when your errors are either large positive or large negative, then there is going to be a large gradient that will adjust the weights of the neural network. So it will train faster to reduce errors that are larger in magnitude. So it may be desirable for many situations to do that, because here the assumption is that this works very well when your error is Gaussian distributed. But when your error is not Gaussian distributed, so your distribution of error, so this is your P of error and this is your error. So we are assuming that it is Gaussian distributed. So Gaussian distribution has certain properties that it is not considered a heavy tailed distribution. A heavy tailed distribution, an example of that would be something like when we have exponential distribution or two-sided exponential distribution, Laplace distribution. So in Laplace distribution, at some point it actually starts to exceed, right, because it is some constant e to the power some constant. So maybe error e and this e are different. So let's just write exp, exp of minus c times mod of e, right. So this is your Laplace distribution, and then there is another constant k, so that these two so that it integrates to 1, or usually we use lambda and 1 by lambda. So here the idea is that for large values of error, no matter what these constants are, the tail is going to be higher than the tail of a Gaussian distribution, where we have e square instead of mod of e, mod of error, we will have error squared inside. So these heavy tail distribution basically mean that there are more outliers, there is more chance of an outlier compared to a Gaussian. So when you have more chance of an outlier, then to try to fit a regression output to that outlier is going to be problematic. So the output or the weights are going to be very swayed by the outliers. So an alternative to the L2 loss is the L1 loss. Okay. So here your loss is basically proportional to mod of E. Okay. And here what we see is that no matter what the error is, the gradient is always going to be constant in the positive side and always going to be negative, constant in the negative side. So it does not get swayed by, it doesn't give undue importance to the outliers. It gives as much importance to an outlier as it gives to anything that is close to the origin. So that way it is a outlier rejection strategy that is for which mean absolute error, MAE or L1 loss are used for regression. And that can also be used for multi-regression, where we can actually look at L1 losses in by taking the L1 norm of the t minus y or the error. Now the undesirable property of this L1 loss is that near the origin it is still giving as much importance to small errors as it is giving to large errors, and by importance I mean the gradient, the magnitude of the gradient. So which is not desirable. So a compromise between L1 and L2 loss, so this is L2 loss which is MSE, mean square error, and this is L1 loss which is MAE. Compromise between the two is that there is a small region in which we use L2 loss. So this is, in this range we will use L2 loss, and outside of that we are going to use L1 loss with a smooth connection here. Okay. So you can easily work it out what that smooth connection is. So this size of the trough we will call it delta. So this is, let's say, up to plus delta and from minus delta. Okay. So within plus minus delta we are going to have a parabolic or an L2 loss. Outside of minus delta, less than minus delta, when the error is less than minus delta or greater than plus delta, we are going to have an L1 loss. So which means that once we enter this trough region, then the smaller, relatively smaller errors will have almost zero gradient, and those will actually not have any contribution in deciding the regression equation. The errors that are outside are going to have an increasingly more gradient, but after some time that gradient will become constant. After a certain error magnitude, that gradient will become constant. So I will leave it as an exercise to derive what this Hubbard loss, this L1 plus L2, it's not actually L1 plus L2, but it's like range wise, piece wise, either L1 or L2, which is called Hubbard loss. What is the expression for that, so that the L1 and the L2 terms, wherever they connect, they are both continuous and smooth. Okay. Now let's look at generalization of neural networks beyond binary classification. So let's say if we have n-ary classes, let's take the example of 3 classes. So let's say we have cats, we have an image which is either a cat or a dog or neither. Okay, so we have 3 classes now. So the question becomes that how do we encode this output, how do we encode this target output, and how do we formulate the loss to train the neural network for a n-ary class classification. So here, so how it works is, first of all, the encoding of this is going to be in 1 hot bit encoding, right. So before this, if we had binary classification, if it was just cats and dogs, cat or dog, then our encoding was we'll pick one of the classes and we will encode 1 if we get that class, and we will encode 0 as if it is not that class. So that is very simple for binary classification, and what that means is that either one of the classes is the base class and the other class is either present or not present, right. It is, if it is not present, then the base class is present, and so it's mutually exclusive, and you need only one output or a scalar output, which is probability of the positive class, and we can train for that using cross entropy laws. Now in n-ary classification, we are going to generalize over that concept, and the generalization is not that difficult, it is just a straightforward generalization. So the first thing is about encoding Ti, right. So let's say if we have, for the ith input we have the target vector Ti, then it is going to be one of these vectors. So it is either going to be 0, let's say 1 0 0, 1 0 0, that means only the first class is present, or it is going to be 0 1 0, or it is going to be 0 0 1. So it's going to be a 3-dimensional vector, but it can be only one of these 3 vectors. This is called one hot bit encoding. If it has n different classes, then we will have n different such vectors, and each of them will have exactly 1 1, and rest of the terms will be 0. That is called one hot bit encoding. Okay. So this is the structure of of T. This in fact encodes a target probability mass function. In that target probability mass function, we have let's say cat, we have dog, and we have neither, and we either have cats as 1 and dogs as 0 and neither as 0, or we have cat as 0 and dog as 1 and neither as 0, or we have cat as 0 and then dog also as 0 and neither as 1, right. So all these 3 have to add up to 1. So our output is going to be continuous, but it has to emulate, it has to try to come close to this T. So this T is now going to be a vector, because you see that there are 3 dimensions here. Similarly, our Y is also going to be a 3-dimensional vector, okay, and basically this is going to be, we will call it as Y1, yi1, yi2 and yi3, or for whatever C number of classes, yic. I will just write it 3 here for simplicity. Okay, so this is going to be the vector Y, and it is going to be such that sum of yij, j ranging from 1 to C, is equal to 1, okay, and yij is greater than equal to 0 and less than, or greater than equal to 0 and less than equal to 1 for all j, for all I and j. Okay, so it's going to lie between 0 and 1. Okay, so that's the probability mass function interpretation. Now we want to bring these two closer. So what we will do is we will try to minimize the cross entropy between these two terms. Okay, so now where does this yi come from? It comes from a generalization of the softmax or the sigmoid function, which is called the softmax function. So what we will have is in the final output, okay, we are going to have zi, and this zi is going to be this vector zi1, zi2 and zi3. Okay, and the only condition on z is that it belongs to the real line. It can be either positive or negative. So this is going to be the output of the previous layer, where it is computed by taking whatever is the activation of the I minus 1th layer, right. We will multiply that with the weight matrix W, Wi, sorry, not I minus 1, L. So let's say I'll just call it A. So we will have some weight times the activation, right, and some bias vector, and that will basically give us this. And what is this activation? This is the output of the previous layer, output of previous layer, last but one layer. Okay. And this can have a different dimension than the dimension of z, but z and y will have the same dimension. Z, y and t, all 3 of these will have the same dimension, okay, which is the number of classes. Now how do we convert this zi, which is an output of a linear transformation of the previous layer to a probability mass function. So we will send this into something called a softmax activation. This is one of those activations which does not exactly work point wise. It looks at all the other activations, all the other activations also. So basically what we have is, we have Yij is going to be equal to e to the power, okay, we are going to have Zij, okay, divided by sum over j is equal to 1 to all the number of classes, okay, e to the power Zij, okay. So what this means is that for the ith output, for the ith input, we are going to compute a probability mass function which is c dimensional. C is the number of classes, here it is 3 dimensional output, and all the numbers are going to add up to 1. How are they going to add up to 1? We will normalize everything by dividing by the sum of all the numbers, which is what you see in the denominator here, and in the numerator we will have e to the power the previous activation for only that class, okay. So now this z can be either a negative number or a positive number, but e to the power z is always going to be between e to the power z is always going to be positive, and e to the power z divided by sum of all e to the power z's is going to be between 0 and 1, and they will all add up to 1. So they will be normalized, and we can interpret now y as a probability mass function, okay. So that is now the interpretation of this is now the generalization of the sigmoid function to n classes instead of just binary classes, and this is called the softmax transformation. Soft, so it's like a max but it is soft. Softmax. What it means is that if one of the z's is much larger than the other, then we will have a max indicator, or we will have Yij equal to close to 1 for that particular Zj, okay. Continue. So that is the interpretation of this Yij, and now we want to bring this Yij close to Tij, okay, and the way to do that is to use a generalization of the cross entropy loss, and this is basically n-way cross entropy loss, and it is very simple. Basically we are going to have a negative sign, and then we are going to have a sum over j, okay, and we are going to have Tij, okay, and log of log of Yij. Okay, this is pretty much it. This is our loss, and then if we want to have it over all the training points, then we might also have sum over I and with a negative sign. Okay, so negative of sum over I, sum over j, and then Tij log of Yij. So now think about how it is working. If Ti is 0, right, so then basically Ti times log of Yi does not matter, it does not contribute, but if Ti is 1, then the loss can only be minimized if Yi is a large value, or large value as in close to 1 as opposed to being close to 0. So when Yi is close to 1, then we are going to have, because of the negative sign, we are going to have 0 loss. If it is close to 0, then we are going to have infinite loss. So the loss profile looks like what you saw earlier, that for different Yij, assuming Ti is 1, it is going to be infinite, and then it is going to come to 0 at when Yij is equal to 1. So that remains as it is, but this is how we will set up n-ary classification. An interesting thing to note about this is that when we take its derivative, and we take the derivative and send it back towards z through the softmax, then basically the derivative with respect to z is quite simple. It is simply ti minus yi, and that is something you can follow the derivation. It is given in many sources. So basically it simplifies quite a bit. Another thing to note here is that if you look at this softmax function and you assume that c has only two values, right? So c can be either 1 or 2. In that case, this quickly can be transformed into the logistic function, except that we will have to take zi1 minus zi2. In those terms it will come out to be a logistic function. So that's if we divide the numerator and denominator by zi1, for example, then we will get that form where we will have 1 by 1 plus e to the power minus zi2 divided by minus zi1. So that it has a close connection, or it's just a simple extension of the logistic function. That is what the softmax activation is. So the reason this is an activation is that activation is always applied over z, right? It's a nonlinearity applied over z, but it requires us to look at all the other activations also, all the other outputs also, the zij for other j, and this is how it is different from other point-wise activations such as ReLU or TANH or sigmoid. Okay. Let's quickly cover another topic, which is metric learning using neural networks. So there are situations where we are neither classifying nor doing a regression, but we are still solving a supervised problem. And those situations are where we know the relative order of some inputs, and we want to predict the order of another input, a test input, but we don't want to give it a very specific output. So an example would be a ranking problem. So let's say we have a ranking problem, right? So here what we have is we have xi and ri pair. We are given these pairs, xi and ri. Ri is a rank or some sort of a order of xi. So for example, let's say you have images and you want to rank them in the order of aesthetic appeal. Okay, so that could be one problem. The other problem could be a verification problem. So you have xi and xj, and we want to basically tell whether they are these two. If we try to find their similarity, then are they similar or dissimilar? That means either we only look at pairwise combinations, and they are either 0 or 1. So 0 means they are not similar and 1 means they are similar. An example application could be face verification, where we have an organization that gives access based on face biometric, and the number of people in the organization keeps changing every day or every week and so forth, and because of that we can't have a recognition system where we have a fixed 1000 classification because we have only 1000 people, because tomorrow we might have 1002 people, and then day after that we might have 998 people and so forth. So what we want to do is we want to maintain a database of a few images of each person, and given that the person is showing their ID and their face, we want to verify that is this the same person as they are claiming to be. So we want to take the test image and we want to compare it with the training images and see whether it is the same person or not. So it is similar or dissimilar. That is what we are trying to do. So here what is useful many times is to take this xi and predict a yi such that the yi is easily comparable. Now this xi, because it is an image or it could be something else, it could be a big vector or a big two-dimensional array, right? So this could be a two-dimensional array, but what we want is we want to change this into a yi and yj which are very similar. These are low dimensional vectors, so that we can simply take their Euclidean distance and see if the Euclidean distance between yi and yj is smaller than a threshold, then they are similar. If it is not smaller than a threshold, then it is not similar. Now here the challenge with doing this directly with xi and xj would be that you cannot take pixel wise difference of images. That will lead to very poor results, because you also have background and you also have eye shades and so forth, or like the glasses, the frame of the glasses and so forth. So two people who have same red framed glasses are not the same, or two people who have the same skin tone or have the same background behind them when the picture was taken are not the same. So we cannot take pixel wise difference. We have to learn something called an embedding. So this yi is now an embedding, and that embedding has to capture this notion of similarity. So what is done in such cases is that we will take a neural network and we will give it an input xi, okay, and we will take the same neural network. Mind you that it is the same neural network, it's not a different neural network, and we will give it the input xj, okay. So these are the same, and the output that we get is yi and yj, okay. And then we will take their Euclidean distance, okay, or we will take their, let's say we will put them in another few layers of a neural network, an additional neural network. So this is NN1 and this is NN2, okay, and the output here could be 0 or 1 depending on whether they are similar or not, and the gradients will flow back through both NN2 and to NN1, NN1 both times, right. So it will, one will come from yi, the other will come from yj. So this is how it can be trained. So because we are using two instances of the same neural network, it is as if they are identical twins that are joined with each other, and that's why it's called a Siamese, based on the term Siamese twins. So this is a Siamese neural network. So there is also something called a triplet Siamese, where instead of encoding whether xi and xj are similar or dissimilar, what we can say is that y of xi, okay, and y of xj are closer than y of xi and xk. Okay, so it's a triplet constraint. That means if we take two images of the same breed of dog, they are closer to each other than a third breed of dog, or a second breed of dog. So we can also formulate it as a triplet where I is the anchor, and then we have a positive instance which is xj, and a negative instance which is xk. So closer than, okay. Okay. So in that case we will have a different kind of a Siamese, and the way that will work is that we will have the same neural network NN1, and it will share weights with another NN1, and it will share weights with another NN1, and the input we will give it is, let's say, xj here, okay, xi which is the anchor, and xk which is the negative sample. So this is the positive sample, this is the negative sample, okay, and this is the anchor, A for anchor, okay. And what will come out of this is yj and yk, and then what we will do is our loss will be a hinge loss over the differences, or over the Euclidean distance of yi minus yj and yi minus yk, okay. So what we want is, so let's say we get these yi, yj and yk, our loss is going to be such that we want to minimize, okay, we want to minimize over max of, this is going to be a hinge loss, okay, So whenever the distance of xi and xj is going to be larger than xi and xk, right, then we are going to penalize that. All right. So this is going to be, and if it is correct, if the distances are in correct order, then we are going to have no loss. So we are going to have a 0 comma. Okay. So now we have yi minus yj. Okay. All right. So this is going to be Euclidean distance. So I will use a okay, and then yi minus yk. Let's write with more space. So yi and yj should be closer to each other. Okay, so we are going to, but if they are not close to each other, then we are going to penalize minus yi minus yk. All right, and then just so that not all yi's collapse to 0, okay, they should not all collapse to 0. That's a trivial solution in which no one will have a loss. So we will have to add a margin here. Okay, so the margin is that it should be safer than a particular margin from this. Okay, so we will subtract that margin, or let's just call it delta, which is a hyperparameter, non-zero, greater than 0 hyperparameter. Right? And then we will sum this over all triplets. So now imagine if your yi minus yk is very large. Okay, it is very large, and it is at least delta larger than yi minus yj. Okay, then there is going to be no loss. Yeah, sorry, it's going to be plus here. Yeah, now this is correct. So we can use neural networks in that way also to do things like ranking or verification. There is a particular problem with neural networks which we try to solve using various layer architectures, and which has led to this the whole revolution in deep learning. The problem is the following, that as we start to add more and more layers in a neural network, there is we will get more and more number of parameters, okay, more and more weights in the neural network, and at some point it becomes too many weights for the number of inputs or the number of training points that we are given. So let's look at it this way. So let's say you have an input, okay, and input has dimension d, and then we start to add hidden layers, and the first hidden layer has n1 neurons, the second hidden layer has n2 neurons, up to, let's say, the last layer which has nl neurons. So the total number of weights that we will have, so remember the weight is a matrix that basically connects every output of the previous layer to every input of the next layer. So here we will have nd or dn1 weights, and then n1 biases. Here we will have n1, n2 weights and n2 biases. Here we will have nl minus 1, nl weights and nl biases. So if we add these all up, you can see that because of let's say if we have 1000 neurons here and 1000 neurons here, this matrix is going to be 1 million, will have 1 million entries. So 1 million different weights is quite large, and suddenly we'll have lots and lots of weights when we start to increase the depth of the neural network, and that is undesirable. So we would like to reuse some of these weights, which is quite in line with some of the properties of natural signals, and using something called a convolution operation, which is what I'll talk about next. So in natural signals, there are two concepts. One is repetitiveness and the other is localization. What I mean by that is, let's say if you look at a crowd of people, right? So this is a crowd of faces, and this is an image of a crowd of faces, right? So they are all attending your lecture, right? So here what you can see is that the shape of an eye keeps getting repeated in different parts of the image. Okay. So if you build an eye detector, it is useful in different positions of the image. Okay. And we can go even smaller than an eye. We can look at the edge, the vertical edge of the face. So this vertical edge keeps getting repeated in different parts of the image. In fact, it may also be used for other objects, detecting parts of another object such as a chair. So this vertical edge may also be a primitive or a small feature that occurs in different parts of the image. Now similarly, we will have horizontal edges and diagonal edges that occur in different parts of the image. The other concept is localization, which means that if you want to look at an object, right, in this object, this eye itself is the detection of the eye doesn't need to look at the entire image, but only at a small locality of the eye. Okay. Similarly, if you want to find the mouth, it is in one small locality, right. So the objects are finite in size, right, and they self-repeat in some sense, or these features that we detect are self-repeating. The same is the case with audio, for example. So let's say this is your pressure wave in an audio. So different phonemes that we talk about. So let's say if we use the word bear, so we have b, a, okay, and r, r. So these different phonemes, right, they persist only for a short time duration. So that is the localization aspect, and they are repeated in other words and other sentences. So for example, pair, that the same phonemes, same two phonemes occur in pair also. Okay. So I'm not looking at the spelling, but let's say if you insist on the spelling, then this is the spelling. Okay. I was trying to write it phonetically, but basically you get the idea that the same thing is localized and it repeats. The other aspect of natural signals is that these localized signals, many of them put together, actually give you a hierarchy of objects and parts. So the objects and parts, for example, a face is composed of different parts of the face, for example, eyes and nose and lips, and then the entire human is composed of different parts, of which face is a part, and then crowd is composed of several humans, and then if you go to a smaller level, then eye is composed of different oriented edges and so forth. Similarly, in natural language, we have documents and paragraphs, and then we have sentences, and then we have words, and then we have phonemes, etc. So there is a hierarchy also. So this repetitiveness, localization, and hierarchy is something that you will see in natural signals all the time. So these are both in audio, in natural language text, in videos, and in images. The other part that you can, the other commonality between them is that these signals appear on a grid, either on a two-dimensional grid, or on a one-dimensional grid, or on a three-dimensional grid. Okay. And the order of samples on the grid, so the pixels in an image or the audio samples on a one-dimensional grid and so forth, that order is important. You cannot switch the order, which is not the case with when you are looking at vector data and you are looking at previously taught machine learning frameworks, where the order of dimensions of the vector, if it is consistently swapped, then it is still meaningful. Here, if you swap the pixel locations, then the image gets jumbled and the shapes are no longer visible. Or if you swap the pressure measurements in an audio wave, then the audio gets garbled and it's no longer perceptible. Same with sentences, etc. So the order is also important here. So this has led to, through evolution, a set of neurons that locally detect features on the sensing surfaces that we have. So one of the sensing surfaces that we have is the retina. So if you look at the eye, so this is the lens of the eye, and then the image forms on the retina, and on the retina, so the light enters here and it falls on the retina, and the retina has these nerve cells that go out into the optical nerve, and then it goes into the visual cortex, the part of the brain where the vision is processed. So in visual cortex there are neurons, right, and they are such that they only look at a local portion of the retina. Each neuron looks at only a local portion of the retina, and it detects a very simple feature such as an oriented edge, whether the edge is vertical or horizontal or diagonal and so forth. And there are several such neurons here. So they specialize in detecting only simple features, but the same feature again and again at different locations of the retina, and they look at a small location of a small spatial compact in which they are trying to detect that shape. They are not looking at the entire retina for a feature. They are looking at a small portion, spatial portion of the retina. They have connections to only a small spatial portion of the retina. So this is found in also in auditory complex and so forth, in our auditory processing system and so forth. So this idea has been used in something called convolutional layers. Let's try to understand that in one dimension, and then we will extend it to 3 dimensions, sorry, 2 dimensions and then 3 dimensions. So let's say we have inputs, right? We have x1, x2 all the way up to x5, and the order of this input is important. So let's say these are pressure measurements of an audio wave at different time instances when we are sampling the audio wave. So we cannot swap x2 and x3. That will change the perception of the audio wave itself, and it will no longer be the way we understand audio. Or similar to how pixel locations cannot be swapped in an image, that order is important. So these cannot be permuted. So now let's say we have some sort of a feature detector where we have some weight W1 here, another weight W2 here, and a weight W3 here. So notice that this is not taking any input from here or here. What that means is that it does not need input more than a small location on that grid. So localization is important, right? And then it is trying to compute that feature. Now because the feature that, let's say the phoneme that we are trying to detect can appear anywhere in time, right? We can shift that entire feature detector, and without changing the weights, that is more important. Without changing these weights, we can shift the entire thing down in on this grid to detect the location of the same thing in another location. So we can basically go from here to here to here without changing the weights themselves. So we reuse the weights at different locations. Okay. So but every time we change the location, we get a new output. Every time we change the location, we get a new output. Okay. So we computed 3 different outputs without changing the weights. That is basically what convolution is. So this shifting or sliding by one location, okay, of the same set of weights or the same filter or the same kernel is called convolution. So this these set of weights with this neuron is called a kernel or a convolutional filter. So basically what it is doing is it is trying to, when will it give you a good high response? So this W1, W2 and W3 will give you a high response when the input that it is examining is also has the same shape as W1, W2, W3. What I mean by shape is same magnitude and sign, similar magnitude and sign as W1, W2, W3, because then we get that square effect and all the negatives becomes positives, two negatives become positives and so forth. So we get high correlation in some sense. So it's a sort of like a correlation detector, and that correlation has is like a dot product, and that's why it's also called a kernel. So this works when your features are local, okay, and their presence or absence is stationary. If you take many images, the probability of finding a vertical edge at a given location is the same. It's not like only left side of the image will have vertical edges and the right side will not have vertical edges. That can happen in things like X-ray images. When you always take chest X-rays, it is the image statistics in different locations are not stationary, because you always look at the objects in the same location in chest X-rays, but in general images they are quite stationary. Whatever, if you take patches in different parts of the image over many images, their statistics are going to be the same. So when the statistics are the same, we call it that it's a stationary signal, and for stationary signals this convolution is a very efficient way of detecting certain features. Alright, so without increasing the number of weights, we have been able to calculate, let's say, 3 different outputs. In fact, we can extend this down further and calculate many outputs, almost same as the number of inputs, without increasing more than 3 weights. So that is the whole idea of a convolutional layer. So now we can extend this to 2 dimensions. So let's say we have an image, and that image has 2 indices for rows and columns. One is I, the other is j, and let's say the size of the image is 224 by 224. Okay. So I and j range from 1 to 224. Okay. And then now we define a window. This convolution, instead of being 3 weights, it's going to be 9 weights, because let's say we can have a 3 by 3 window now. We are going to look at it in 2 dimensions. So our weights are going to have also have 2 dimensional indices, u and v, but it is a it's a 3 by 3 window, so it has 3 indices, -1, 0 and +1. I will talk about it more in a little bit, but let's say these are the 3 indices. Okay. So if we want to have the sliding effect, okay, so first of all we are taking the correlation between w and x, okay, and that correlation is based on a sum product of wuv and xuv, but we can shift xuv, the index of x, to any location I and j. So xi plus u and xj plus v. Okay, so these are the 2 indices, and we will take that correlation and we will compute that, so, and that will give us for one output location which is at ij location. Okay. And then we can add a bias, and we can send this pointwise through a sigmoid or a tanh or through a ReLU. Okay. So those things can also be done. So now let's see how that is visualized. So let's say this is any ijth position, this is I and j position, okay, and here we have the pixel xij, but now we have a small window around it, a 3 by 3 window around it, and our kernel which is sliding over it, which is wuv, is also 3 by 3. So if I take this element and this element and I will multiply them, then I add it to the product of this element and this element, product of this element and this element. So I will get 9 different products that I add up, and when I add them up and add a bias to it, what I will get is one term zij. Okay. Then I can shift it to the right, I can shift it one portion to the right, and then I will get the next product. Then I will shift it one more to the right, and then I will get the next zij and so forth. Okay, so I am sliding it right. When I reach the end, then I will go down by one step and again start sliding it to the right. So I go either one right or one down. Okay, so that is the convolution in 2 dimensions, because I have this dimension and this dimension to take care of. Okay. So this is how I will get all the outputs. So you may be wondering what happens at the edge. So we have 2 options here. One option is that we don't go beyond the edge. The other option is that I pad the edge with 1 extra value of zeros, so that I can also go beyond the edge, and then I can have the same size output as that of the input. So those are just nitty-gritties of convolutional layers, but basically these layers help us detect different uh, different what do you call it, different features that are localized in the image. So for example, one W could be detecting vertical edges, another could be detecting horizontal edges, another could be detecting diagonal edges, and we could be sliding it all over the image. So now, what is also clear is that just a single W is not useful. We need multiple Ws. For example, we want to detect edges of multiple different orientations. So this, we will modify the convolutional operation to bring in some new indices. So let's say our input is not just I and J, but input have multiple channels. So for example, an image has 3 different channels, red, green and blue. Okay. So the channel is now described by the third index, which is K, alright, and now the output itself has more than one channel, which is M different channels. Why more channels? So this is the number of feature detectors that we have. So for example, if we want to detect this edge, this edge, this edge, this edge, this edge, this edge, this and this, etc. So we need 8 different channels, and perhaps the negative of all that also. So for example, going from dark to light and light to dark and so forth. So we need multiple different channels. So the output will also be multidimensional for each location of the input. So the way this will work is that we will have mth channel for the output also, and ith location and jth location, ith row and jth column. Okay, and for that we will run a sum over the size of the filter as well as number of input channels, okay, which is k. And we will have, now your weight has 4 dimensions, okay, u, v, or 4 different indices, u, v, k and m, and then the input that we had has 3 indices, just like we had here, I, j and k, but I we will offset it by u and j we will offset it by v. Okay. So to visualize this, what we get is something like what is shown here. So these number of channels that you have are k channels. This is I and this is j. All right. Here we have u here and we have v here, and the number of channels, because this has to fit exactly onto the input, this is going to be k. But then we have multiple kernels, one detects horizontal edges, the other detects vertical edges, etc. So these multiple kernels, this second kernel, the index for the kernel is going to be m. Okay. So now I have output, I have m different outputs, okay, and again the indices are I and j. Okay, so I get 2 different feature maps, one for each kernel, okay, and the size or the depth of the kernel should match the depth of the input, the number of channels of the input. Okay. So this tells you how many trainable parameters in this you have. The number of trainable parameters you have is 3 times 3 times k times m, and then you have one bias for both of these neurons. So we will have 2 biases also, or m biases also. So once we set up these convolutional layers and we even initialize them from random numbers, we initialize them from scratch without telling the neural network what to detect, it turns out that once we train these neural networks, the convolutional layers naturally learn some primitive features that are very similar to how the visual cortex of mammals is. So we have edge detection neurons in the V1 layer that detect edges in various orientations, and it turns out that if we plot the two-dimensional array of the weights that are learned, let's say if we have a 7 by 7 filter or something like that, or 11 by 11 filter, and we plot them, we visualize them as shapes, then we get these oriented edges. So for example, you can see here that here you can see that here edges of different orientations are being detected in the convolutional layers that are learned organically from natural images. You'll also see that there are color detectors, because color also seem to be important for visual recognition for image analysis tasks. So these are all based on neural networks that were trained on image recognition with random initialization. So what comes out of these images of these convolutional layers is something called a feature map, right? So what is a feature map? So let's say you have an image, right, and this image has a face, okay, and I have a small kernel that detects vertical edges, okay. So by light I mean that it has positive weights, by dark I mean it has negative weights, and I convolve it over this image. So I will get another two-dimensional matrix which will be roughly of the same size as the image itself, and it will detect all the vertical edges, okay, and it will give me zero response on the horizontal edges and in the flat portions of the image where there is no where there is no where there is no variation in the pixel intensity. So here you can see that once I superimpose this particular kernel here, then there will be high correlation with the way the weights are, the shape of the weights, or the way the weights are spatially organized in this kernel, and because of that I will get a high response, and I will get these vertical looking the numbers that form a vertical shape in the output of this convolutional layer, of this convolutional kernel. Whereas here the because we are cutting this convolutional kernel in the middle, we will get a zero response, the top and the bottom will cancel out, and because of that we will get nothing here, right. So because of this, when you look at the response of the first layer, different kernels of the first layer, you will see that these are the vertical edges that were detected, these are the horizontal edges that were detected by another neuron and so forth, another kernel and so forth, and these are perhaps could be some texture or some color that was detected and so forth for some particular image. So this is for the first convolutional layer. After the first convolution layer, things become more complicated if we stack convolutional layers on top of each other. So as you can see that the output itself is a two-dimensional array, so you can run another set of convolutional kernels in the second layer and so forth, and they still maintain some sort of a shape detection type characteristics, but very soon it starts to get lost. So and then the response becomes more and more localized as opposed to like continuous edge detection and so forth, because now you are now we are detecting combinations of features, combinations of edges and so forth, which could be corners, and they are very spatially localized in one part of the image. So that is and then after that, if we go to convolution layer 3 and 4, then the feature maps are very difficult to interpret. You will just see dots, isolated dots. So those could be, for example, eye detection, so it will give you response when it has detected an eye, or a nose detector and so forth. We don't know what it actually detects because they are all trained from scratch, and we let the data determine what is to be detected. Okay. So but before we get into that in more detail, let's look at the principal advantage that we got by using convolution over not using convolution. So let's say if we had an image of size 32 by 32 and it had three channels which are R, G and B. So now we have a three-dimensional array or a three-dimensional tensor of size 32 by 32 by 3. So let's draw it like this. We have 32 by 32 and we have 3. Okay. And from this, from these many numbers, we want to detect a feature map, okay, which is slightly smaller because we don't want to go over the edges. So it is of size 28 by 28. Okay. So this is 32, 32, and this is 28 by 28 because we are using a 5 by 5 kernel, all right. And but we want to detect 25 such features. So the depth now has increased to 25. The number of channels has increased to 25, whereas originally we had only R, G, and B, red, green, and blue, 3. Okay. So your hidden output is 28 by, or the output of the first layer is 28 by 28 by 25. So if all of the inputs were connected to all of the outputs, the number of weights we would need is 32 by 32 by 3 times 28 times 28 times 25, which is around 60 million weights. That is a huge number of weights to be calculated. The advantage of having so many weights is that you can have a separate feature detector for any location, and it is not even location specific, it actually can detect large shapes from different portions of the image, whereas that's not how mammalian vision works. We detect same features again and again, and to detect that feature we look at only a small neighborhood. That is basically what convolution is about. So if we were to do convolutions, which is weight sharing, we would have a feature of size how much? We would have a feature of size, we would have a kernel of size 5 by 5, let's say, and because it has to examine all 3 input channels, we will have times 3, and because there are 25 such features, times 25. So we have only 1875 weights. Okay. So that's a huge reduction over 60 million. I have not even counting the biases. The reduction in biases is smaller, but in the number of weights, there's a huge number of reduction in weights. There's a large extent of reduction in weights. So what that means is that I can stack many more layers without having an explosion in the number of weights, and that also has a regularization property in the sense that we are forced to detect useful features, features that are useful irrespective of location, so that we make better, more efficient use of the weight budget that is given to us. These are some primary reasons behind the success of convolutional neural networks for image processing. So how will backpropagation work? In this case, because we have an image, right, and we have this kernel, and this kernel not only operates at this location, it also operates at this location and at this location and so forth, to give you this output, this output, this output on the entire output feature map, right. Because of that, all 3 locations are contributing these outputs, all 3 outputs are contributing, and consequently all these 3 inputs, right, are contributing to the gradient descent of the gradient of these weights with respect to whatever is the loss here, okay, after stacking many layers. So basically your backpropagation is not going to treat only each image as a separate sample, it is going to treat each location within the image also as each pixel location also as a separate sample. So all of them are contributing to the tuning of every kernel, and each kernel you can think of it as a repeating neuron. Okay, so it will treat each input patch and not just a sample as something that is contributing to gradient descent. So the other thing that we have been neglecting till now is that we have been very focused on detecting local features, but when you put several local features together, the extent of what we need to detect, the spatial or temporal extent of what we need to detect becomes larger. So what that means is that with small kernels of size 5 by 5 or 3 by 3 or 11 by 11, we can detect small things like edges. But if we want to detect like a complete face, or want to do face recognition or something along those lines, then the number of pixels that we have could be much larger than, let's say, what a kernel can look at. So we need to be able to detect we need to be able to have outputs that are affected by a large area of the image. So now if we have several layers here and we take one particular output, okay, in every layer we have a two-dimensional grid of outputs. If we take one of those outputs, then the footprint that we have on the original image, where if we change one number we can potentially change this output, right, that is called receptive field. Receptive field. So an example of this would be, let's say if we have a 3 by 3 kernel, right, if I have a 3 by 3 kernel and then I have the output and I look at one particular output here. So for this particular output, I can only change inputs in a 3 by 3 neighborhood to potentially change this output via this kernel. Okay. Now on top of that, if I have another 3 by 3 kernel and then I get another output feature map, right, and I look at one particular output, its footprint here is a 3 by 3, but then its footprint here is going to be a 5 by 5. Right. So the receptive field of this neuron is 5 by 5, whereas the receptive field of this neuron is going to be a 3 by 3. Now we want these receptive fields after a few layers to be very large so that it can look at big objects and do some processing on those objects, or basically recognize those objects or detect those objects and so forth. Now the challenge with that is that requires many convolutional layers to be put together, whereas we may want a faster way of detecting, of increasing the receptive field. By faster I mean within a few layers we may want to increase the receptive field quite a bit, and while doing so, the parts that we detect, their exact location is not important. As long as they are detected, they are fine. So what that means is, if this eye is slightly shifted to the right, it is still a face. So the exact location of the eye is not important. I want a little bit of a translation invariance to the location of the eye, okay, and scale invariance. The face can be slightly bigger or slightly smaller, eye can be slightly bigger or slightly smaller, it is still a face. So for that, a second type of layer is introduced, which is called a pooling layer, and that is a local summarization layer. So what it does is, let's say if we have a feature map of size h by w, we want to just reduce it to a smaller feature size of size, let's say h by 2 and w by 2. And what we do is we take a 2 by 2 neighborhood and we just summarize it either by taking an average or taking a max and plotting it in one location. Okay, so that is called average pooling or max pooling. So the math would look like this, that you have xij, where ij run from, let's say, 1 to 224, and we have yij, which is basically nothing but average of a small 2 by 2 neighborhood or a max of a 2 by 2 neighborhood. So there is nothing to learn, there are no parameters, it is just a fixed layer. It just tries to reduce the size of the feature map. Consequently, when you have another conv layer after that, convolution layer after that, the receptive field of the activations of that output of that convolution layer will increase at twice the pace than the one that was before pooling. Okay, so the way we would visualize pooling is that, let's say if this is xij, we would take a small 2 by 2 location, and with that we will just summarize it and plot it here, and then when we will compute the next pooling location, we will not move by 1 but we will move by 2. So now we have non-overlapping stride. Before that we had an overlapping stride, so again we will have something like this. So as you can see that the size of the yellow squares, the number of yellow squares is going to be 2 by 2 less than the number of red squares. So the feature map that we will get is going to be w by 2 and h by 2, where this is w and this is h. So that is called a 2 by 2 max pooling. You can also have 3 by 3 max pooling, where the size reduction is even further. So here basically why we do max pooling or average pooling is that if an eye is detected, okay, and eye detector gives you a high, so let's take a 2 by 2 neighborhood. If one of these value is high and the other values are very low, right, That means I has been detected in this 2 by 2 location. So before this we had an eye detector, so this, the shape of this matrix was such that it was detecting eyes. So one of them, so it has detected that eye in that in that 2 by 2 neighborhood. That is good enough for us. We will just summarize it as one detection. We don't need to look at whether it was slightly to the left or right, or whether it was slightly bigger or smaller. So basically a typical CNN architecture would be that you have an image, and it could be a color image, okay, and then you would have a convolutional layer. So you will have several convolutional filters, and based on that you will get the convolutional feature map. Okay, and then you will have another set of convolution layer. Sorry, after this you will have a pooling layer. So usually you will have input, okay, conv, pool, conv, pool, etc. So several conv pools together, and then you will get a very small feature map. So that small feature map is, so for example here after that, if I do pool, the feature map is going to be of a smaller size. Same number of channels but a smaller height and width, and then again conv and pool, and then it will become smaller and smaller. So at some point it will become very small. Number of channels will increase. This is number of channels, and but the height and width is going to be very small. So h by 128 by or w by 128 by h by 128, let's say, right, some power of 2. So it has become quite small. So once it has become quite small, there is no point in doing convolution, because you cannot move left and right on a very small feature map. So because you cannot do that, you will just take this 3-dimensional tensor, stretch it out and make it into a 1-dimensional vector of size whatever, h by 28 by w by 128 times whatever the number of channels, and then we will have, after this we will have fully connected layers, just like a regular neural network, and they will give you the output, which will, the final layer will give you the classification or whatever regression that you want to do. So this will be fed into a fully connected layer. So after that, the same kind of principles apply, that they are the weights are organized as matrices, with the number of inputs being the total number of outputs of the previous layer, and so forth. Okay. So after that we have what is called dense layer or FC layer, fully connected or dense. It is also called dense layer. So several of these, okay, until we get the output, which is also a dense layer. So that is a typical CNN architecture. The other thing to note here is that the size of the feature map, okay, size of feature map is decreases, but number of feature maps increase. Number of feature maps as in the channels increases, and that is because there are more complicated parts to detect, and there are more types of complicated parts as you go deeper into the network. Okay. But to detect those complicated parts, we have to look at larger and larger receptive fields on the original image, and because of that, the size of the feature map, the spatial size, the W and H decrease, but the number of channels, which is C, which is the RGB here, just 3 here and let's say 25 here and whatnot, that keeps increasing. So now CNNs can not only be applied to images, but they can also be applied to other types of data such as speech. So let's take an example. In speech, what we have usually is something called a spectrogram. So we have the time dimension here, okay, and because of that overlapping bands of frequencies based on Fourier transform, we will have frequency here. Okay. So what one particular window means is that at that particular time, what is the contribution of a particular frequency range. Alright. So different phonemes will have a different frequency temporal structure. Now here, and this is on a log scale. This tessellation is on a log scale, okay, and but time is on a linear scale. So here we can detect same existing feature, which could be like some sort of a speech pattern, either at high frequency for a high pitched person or at a low frequency for a low pitched person, and either earlier in time or later in time. So the same kind of a localization and repeating pattern principles apply for speech also, and we can use CNNs for speech. Okay. Just as the size of the filter is going to be tailored towards what is the typical size of a particular feature to be detected in speech as opposed to images. Okay. So CNNs can also be used for speech. They can also be used for other data, such as we can have one dimensional CNN as opposed to two dimensional CNNs for processing DNA sequences, for processing protein sequences and so forth. So they have variety of applications. I'll take one more example of CNNs being applied to text. Okay. So if you have a text, the way to encode text is again using 1 hot bit encoding, but it's a slightly cumbersome to encode it as 1 hot bit. So what is text basically? For example, the bear was charging. Okay. So this sentence has 4 words, right, and these 4 words are, and you can have text with various lengths of words. So to encode each word, so here the unit is not a pixel, it's or a pressure point, it's a pressure measurement sample, it is a word. So to encode this word, we would have a giant vector, and the number of dimensions in that vector is going to be size of dictionary. Okay. And only one of them will be 1, rest of them will be 0, 1 hot bit encoding. Which one will be 1? Where whatever is the location for the word the, and similarly the next vector will be for bear, next will be for was, the fourth one will be for charging. So we will have 4 vectors, and each of them will be 1 hot bit encoded. So now you can think of it as a sequence of vectors where each column is 1 hot bit encoded and different locations are 1. Etc. Right. So this is your location of word, and this is your lexical order or lexicographical order in the position in the dictionary. So now I can treat this as a 2-dimensional input, and I can apply convolutional neural networks to it, but it doesn't work very well with that. What might work better, so first of all, this dimension becomes very large, because we are, let's say if we restrict the dictionary to 10,000 words, even then it is quite large. So the first thing that is done is to convert this 1 hot bit encoding into a smaller vector, but it is a dense vector. It is no longer a sparse vector where there is only 1 and rest of them are 0. It is a dense vector. So these are numbers like 0.34, 0.56, etc. And the dimension is going to be small. This dimension is let's say around 300 as opposed to 10,000. Okay. And it's a dense encoding, and this is done by a separate neural network called word embedding neural network, such as glove or word2vec. So I'll just give you these terms. These are for an advanced course. So let's say a glove neural network, and that will give you this encoding or embedding. And once we have that, then there are special CNNs that are called transformers, which have some other special kinds of layer like self-attention layers that can operate upon this, and they can actually even process text, not just speech and images and videos and MRIs. So videos will require a 3-dimensional CNN and so forth. The other layers that you should know about, which are beyond the scope of this course, are dropout layer and batch normalization layers. These are layers that help train very deep neural networks by getting them sort of unstuck in their gradients to be unstuck, in the sense that so if you have a dropout, basically if you have a bunch of neurons and then you have another bunch of neurons in the next layer and so forth, right, and they are fully connected or they are convolutionally connected or whatever that is. During training, we randomly take some neurons and drop them out, and there is a dropout probability. There is a probability by which they are dropped out, and there are heuristics for what is a good probability for what type of layer and what location of the layer. And by dropping, what that means is that the reliance, the codependence on two neurons in the same layer is broken, or any two neurons is broken, and we have to keep training assuming that this particular neuron is not reliable, and because of that the other neurons learn independently useful features. So that is the main idea behind this. Another layer is batch normalization layer, where when you have very deep neurons, very deep neural networks, and all these inputs are flowing in this direction, then for one particular neuron the gradients can be very small or very large. So what it does is it catches it takes the outputs of all the batches, the gradients of all the batches, and it normalizes them again. So basically it rescales them and it learns the scaling parameters also. So that helps the neural network train faster and not get stuck because of very small gradients in some deeper layers and very large gradients. Other concepts that are useful for neural networks is that we were looking at only one layer at a time, but many times there are two parallel layers or two parallel paths that can exist in more advanced neural network architectures. So for example, what we have seen is that you have a previous output and it goes through a feature extraction, which is nothing but a layer, right? So it could be a fully connected layer or it could be a convolutional layer, and we get an output. But in something called residual networks, we take the same input and we add it to that particular output, which means that the number of channels that you will have here and the number of channels in the input are going to be the same, only then you can add it. The advantage of that is that if the weights here are too small and the gradient gets stuck, the gradient has an alternative path to train the lower layers. Similarly, we can have two layers. We can have one set of convolutional filters here, another set of convolutional filters here, and then we can concatenate their output. This is a particular approach that was taken in inception networks for image processing. Another type of layer is that we send the input through one feature extraction. This could be a convolutional layer. We could have another convolutional layer, but here the output is not sent through a ReLU activation. So this is, let's say, through ReLU. This one is sent through a softmax or a sigmoid activation, and then basically it acts as a 0 or 1 gate that gets multiplied to allow this to flow or not allow this to flow, and that is called attention. So it basically says that whether we should put attention or not put attention, because this output is going to be between 0 and 1, whether to put attention or not put attention on one of the outputs from the other branch. Okay, so that is called attention type parallel connection. So these are all parallel connections. So the layers need not be only in a sequence, they can also be, some layers can be next to each other parallelly. Another concept is something called multi-headed neural network. The idea here is that you may have one input to a neural network layers, but then you can give the output to two different other neural networks. And these could be very small neural networks, and you have two different outputs and two different objectives, both of them are sending gradients back to the original neural network or the original set of the lower set of layers. An example would be, let's say we have an image and we not only want to localize the object, we want to do a regression on the object. So this could be a regression, bounding box regression. So this regression gives you the xmin, xmax, or the location min, location max, and so basically the four corners of the detection box, right. So this will give you 4 numbers. You are doing regression on 4 numbers to find the box that encloses the object, and here we are doing classification to say which class of object is it. Is it a horse or a dog or an elephant and whatnot? Okay. So we can have 2 different objectives, and those are the 2 different heads on the neural network. So we call this NN1 and NN2, but actually it's the same neural network with 2 different branches, so to speak. So those are multi-headed neural networks. So there, because all of these are end-to-end differentiable, a lot of these different configurations are possible. So here, if we go back to the side branches, again the gradient coming back will go to both sides, right. The gradient coming back will go to both sides, and here only here one has to be careful that now we have to apply chain rule to a product of 2 functions, which we haven't seen before, but it's not difficult to figure out, and I will reserve that for a future course. All right. Now there are situations where we want to not treat each input of a neural network as independent from another input. Until now we have been assuming that they are IID, independently identically distributed, but let's say the input, each input, actually the training samples come in a sequence. Okay, this sequence could be a sequence of words in text, or it could be a series of sequence of stock prices in a time series and so forth. So for time series and for natural languages where you have an order of words, we need some special structures to map long range dependencies. So for example, if we are talking about natural language processing, the words at the end of the sentence could be related to words at the beginning of the sentence or even the previous sentence. So for example, if I say that Lisa went to the kitchen, she picked up a knife, so she is now related to Lisa, which was actually in the previous sentence, or it could be multiple sentences before. So it's a very long range dependency to disambiguate what is she, right, and or who is she, and this long range dependency is something that goes beyond convolution and pooling. So we need a concept of a memory where some of these important nuggets of information can be stored once they are extracted by a neural network. So this brings us to something called a recurrent neural network. So these recurrent neural networks they remember and they pass the information to future inputs. So for example, let's say we have an input xn at time location or time instance n, and we are trying to give an output yn, right. Now here internally it will compute some intermediate output h of n, but that h of n will act as an input to the future x of n plus 1. So when that is processed, this will act as an input to that. Similarly, for this particular input, the previous hidden state is going to be another input to the neural network before we get the output. Okay, so the h is dependent on not just x but h of the previous time instance. So here's what the sequence might look like. So if we have x of n minus 3, we will get h of n minus 3, which goes to computation on x of n minus 2, which gives you h of n minus 2, which goes to the computation on x of n minus 1 and so forth. So this state, hidden unit output, is sent forward in time and it's a remembered state. Okay. Another way of looking at it is that we have this computation of h of n from the input xn, and then it is sent to a time delay and it comes back. when we are it comes back as h of n minus 1 for the next state. Okay, so these are different ways of looking at the same thing. So the internal structure will be that we will have an n dimensional input, okay, and we will have, let's say, an c dimensional output, or a dimensional input and a c dimensional output, and a b dimensional hidden unit, right, and they are all getting inputs from the previous time state. Okay, so the input to this is not just x but also h of n minus 1, and they are all fully connected. Right. So just to revise non-recurrent neural networks, we will have an input, it will be multiplied with a weight matrix x of x, w of x to h, wxh, and then it will be sent through some non-linearity, we will get the hidden unit output that will be multiplied with another set of weights from h to y, and then let's say if it is classification, then it will go through a softmax non-linearity, and then we will get y. Okay, so this is a regular neural network without recurrence or memory, and it gets changed to something like this, where we have the input and we have the previous state, and then we get the output. Inside this, what is happening is that we have a weight that multiplies with x, but then the previous hidden state gets multiplied with another set of weight, a weight matrix. This is a square weight matrix. This need not be square, this can be rectangular, but this has to be square because it is acting upon the it is taking the previous hidden state of whatever dimension it is and producing an output of the same dimension. So it's a square matrix, and then this also need not be square, this can be rectangular, that the one that is helping us compute the output. Okay, and then that is again sent through a tan h nonlinearity. Need not be tan h, we can actually also have other kinds of nonlinearity, but this is just for the sake of argument. So how this will be trained is during back propagation, we will start to send the gradients back. So we will compare this against some target value Tn, and based on the loss we will send the gradient back. That gradient will be now sent back here, and from here it will be sent back to tune these weights, and it will be sent back here to tune these weights. Okay, and to tune these weights, some gradient here is also coming back, which is from future, from that future time instance. Okay, so that is called back propagation through time. So now if we unfold this entire time, unroll the time, right, so this particular, the difference between Tn and Yn, or whatever is the gradient here, is being propagated here to tune these weights as well as to tune these weights, and through these weights it is being tuned, it is tuning w of xh again, and it is tuning this w of hh again, and so forth. Okay, so these are only affected by one output, the w of hy, but w of xh and hh are being affected by several outputs. So we cannot have them be affected by infinite number of outputs if we have a very long sequence. So we just limit it to, let's say, a window of 50 or 100. Within that window we will tune it for every output, okay, and it will back propagate back through time. Now this creates a problem. Okay, this creates a problem which we will see very soon, which we need to resolve. Okay, so the mathematical expression for this for back propagation through time would be that if you have an input, it gets multiplied with some weights, and then it also gets input from the previous time instance. So for forward propagation, this will go into the activation function, then we will multiply it with the second set of weights and send it to another activation function to compute y. Now if we take the back propagation, then what is the derivative of y with respect to w11, right? So here we are taking the chain of partial derivatives. So it is going to be g dash w to hn dash, and when we expand hn dash, the derivative of hn, then what we get is something like this, and within that we have hn minus 1 dash also. Okay. So because of that, what we get is this entire path where the derivatives keep coming back and they keep getting multiplied with WHH. So basically, if your WHH is kind of large or kind of small, if it is large, then several large weights will get multiplied with each other and we will have an explosion of gradients. If we have WHH to be small in magnitude, then several of them will get multiplied and we will have a vanishing gradient. So we have either a vanishing or an exploding gradient problem. So to control that, we should not have a path where weights are repeatedly multiplied by themselves or with other weights. We should have some way of modulating what gets multiplied, and that is precisely the problem that long short term memories try to solve. Okay. So, and this problem actually also exists in deep neural networks like convolution neural networks, where we are not multiplying the same weights again and again, but we are multiplying weights of different layers while computing the chain rule of the gradients. So for example, for the lth layer, we have WL times f, the activation function of L minus 1 times WL L minus 1 and then WL minus 2, etc., etc. So when we take the gradient and we go deep into try to compute the gradient for one of the deeper layers closer to the input, all these weights will get multiplied with each other, and because of that, if the weights are too large or too small in a sequence, then we will have a vanishing or an exploding gradient. The way to check that in convolution neural networks is careful weight initialization. So there is something called Xavier initialization or Kamenhi initialization. So that should be carefully followed while initializing the weights of deep convolution neural networks. The recurrent neural networks have a different problem, that it's the same weight matrix that gets multiplied, it's not the weight matrix of different layers. Because we are sending it back through time, the WHH gets multiplied with itself multiple times. And to avoid that, there is a special structure that was proposed by Graves et al. And in this case, basically we never sent the error back through the same set of the gradient back through the same set of weights again and again. So here each arrow is a weight. This is one hidden neuron of an LSTM, and basically the way it works is it works on this multiplication type of operations which we haven't encountered so far, which I just alluded to when I was talking about attention layers. So here every input, so this particular neuron has one input that is coming from, so it has three different gates, let me put it this way. So we have an input gate, okay, and we have a forget gate, and we have an output gate. What is a gate? Gate, basically its output ranges from 0 to 1. It has a sigmoid activation. So all the three F's have sigmoid. F is equivalent to sigmoid. Okay, and here the input, so the output of these gates ranges from 0 to 1. So it basically either allows the other input to flow through or it stops it. So similarly, this input either allows this to flow through or it stops it. It lets it flow through when it is 1, it stops it when the output is 0. Similarly, this allows this to flow through or not flow through. So that is the idea, and because of this multiplication, now that chain of W's getting multiplied with each other, that gets broken. So now these gates either allow or disallow input, allow or disallow output, allow or disallow remembering of the state itself. So there is an internal state which is not accessed. So whether it will come back in next in time. So these circular arrows means it is in the next time with one delay. So here there is a delay element here. So it will get either remembered, or it will be overwritten by whatever is the input. So it will either remember what it has, or it will pick up the new input and process that. And there are several of these neurons in the hidden layer. Because of that, it can remember high dimensional encodings of the input. So I'll not go too much into the detail, but basically these are some of the problems with neural networks that have been sequentially been resolved by different newly proposed neural network architectures and deep learning paradigms that has allowed us to process text, to process time series, to process images, to process videos and medical data and speech and audio at an astonishing rate in the last 10 years. With this, I come to an end of this lecture. I hope you enjoyed what I taught about long short-term memories and convolutional neural networks. Thank you.